Let's have a huge round of applause, ladies and gentlemen.
Huh? Let's get back to the beginning. There we go. Hello, everybody. I want to thank you for coming back. I want to thank Mr. Tombe and the Steel Group for putting on this auspicious event. A lot of very interesting information today. But we're going to do something completely different. We're going to talk about sealer. There's been a lot of talk today about corrosion, and sealers are used extensively throughout the body making process for the sole purpose of preventing corrosion and extending the life of the automobile. So let's start by taking a look at the history and how it came to be. Now, I'm from Detroit, where this whole automotive thing started. And prior to the 1980s, rust was just a part of the life cycle of an automobile. And it started in the rocker panels and the lower doors. It spread to the floor pans. And then the wheel wells raced the bumpers to see who would fall off first. And even the hood, the deck lid, the roof, no part of the car was exempt from rust. When I learned to drive, which by the way was a long time ago, we joked that our cars were already rusting when we drove them off the dealer's lot. We thought there was two good things to do with Coca-Cola. You could quench your thirst, and you could use it to remove rust from your bumper. But this created opportunity. Aftermarket places sprang up that would undercoat your car to try to prevent rust. But this was a clunky technology. They would drill holes, they would spray sealer inside, and then they plug those holes. And the auto manufacturers understood the problem. They even offered undercoating as a service for a while they searched for a permanent solution. With the rise of modern sealer technology, sealer could be placed in those areas that were most susceptible to rust, and therefore they could extend the life of the car. Originally, these were applied manually, but there were problems with that. But this was the 80s, and the 80s was the age of the robot, and robots were being used to automate everything. All those precise tasks that were repetitive in nature that people just get tired of doing were delegated to the robot. And this was perfect for sealer because a robot can run the same path at the same speed and hold the nozzle the same distance and angle to the part, dispense after dispense after dispense. But it lacks something important. It lacks eye-hand coordination. A robot can't watch the bead and compensate for those changes in viscosity that come from changes in temperature. And it created multiple issues. And for a while, it looked like maybe this wasn't an ideal robotic application after all. Then in 1990, Clair Systems came on the market with a bunch of different devices and methods for controlling sealer temperature all the way to the point of dispense. And this was a game changer. Now, morning to evening temperatures, season to season temperatures no longer affected the application of sealer. And the rest is history. Today, virtually every automotive body shop has robotic sealer applications. And virtually every one of those successful applications has some form of temperature control to stabilize the sealer. Now, here's a case study. Tata Motors was experiencing problems in their body shop. And they were certain that the problems were caused by changes in viscosity resulting from changes in temperature because of seasonal and daily changes, like I just discussed. They tried a bunch of different solutions, including formulating an all-season sealer that wouldn't respond to temperature changes. All of these solutions were less than desirable result. So in April of 2012, they came to us and said, we'd like you to examine our systems. Look at what's going on. We're facing a product changeover, a new model coming online, and while we're making these changes, we want to make those changes that will solve the problems that we're having. So we went in and we looked at the systems. We did interviews with people in the body shop. And those interviews revealed some interesting things. We went in expecting to find issues with sealer bead quality, and we did. That was no surprise, but the real surprise came in that the real underlying problem was that they had recurring pressure faults. They were frequent, they were intermittent, and they were unpredictable, and they were causing line stoppages. And these line stoppages were disrupting their production process. It was limiting their throughput, and it was restricting capacity, none of which was acceptable with the new model. So, armed with this new information, we went back and looked at the system again. And we said, let's look at what's really here. And what we found was that the header piping that ran from the pumping stations up overhead and along the floor over to the dispensing cells were comprised entirely of 25 millimeter uninsulated piping. Now, this is a problem because when we looked at these cells, these runs were between 20 and 25 meters long. And this meant that we've got this little core of material running this long distance, surrounded completely by steel out in the ambient air. This was a giant heat exchanger, and the air was trying to change the sealer of the temperature of the sealer, let's get that right. And so now we knew the fundamental of the problem, especially when we considered Pune, 145 kilometers southeast of Mumbai at an altitude of 559 meters. The Pune climate ranges from less than 10 degrees C in the winter to greater than 40 degrees C in the summer. And if we look at this chart, you can see around February and March that while we see over 30 degrees shift from season to season, we see upwards of 20 degrees of shift in some of those seasons just from day to night. So you can have that 20 degree C shift all in one day. Now, we calculated the dwell times in the piping for each of those systems and found them to be between 36 minutes and 100 minutes, depending on the system. That meant that it's the sealer spending a long time in this steel heat exchanger exposed to these changes, constant changes of ambient temperature. So from there, we had to figure out what was going on, but we already knew. It's all about viscosity. All liquids change viscosity as a function of temperature. This happens to be an old chart of water. And most people don't realize that water changes viscosity by a factor of 2 to 1 between 10 and 40 degrees. You don't think of your glass of ice water as being thicker than your cup of tea, but it is. And all sealer materials follow this same pattern. So much for the concept that waterborne sealers don't require temperature control. But the thing about it is that this is a physical property, not a defect. And as such, it's repeatable. And as such, we can use it as a tool in our process to control the result of our dispenses. Now, this is a typical sealer viscosity versus temperature curve. We've all seen these before. As the sealer gets warmer, the viscosity falls. As the sealer gets cooler, the viscosity increases. Now, if you couple this with the temperature swings that we're talking about in the Pune area, you can see that we have major swings in viscosity. And those major swings in viscosity were what was causing the pressure drops that were causing the pressure faults. Now, this affects all systems, every sealer system out there, but there's some common solutions that are generally employed to compensate for this kind of situation. Usually you start when you're running 20 to 25 meters, you run large headers, 50, 75, even 100 millimeter. And these are often determined by both the length of the run and even the viscosity of the sealer that we're pumping. These are complemented by smaller drops. And in fact, that 25 millimeter pipe that was used throughout the entire system is commonly used for a drop from the larger header down to the dispense. And what that does is it creates a differential pressure drop, and it tends to dampen the pressure variations that we're seeing in the header. And that gives us a more consistent pressure delivered to the regulator and onto the sealer system. This mitigates those temperature-based viscosity changes. It doesn't eliminate them, but it does tend to reduce them. So why not, if we're doing a product changeover, just go in and change the header piping? We're going to tear the place up anyway. But you see, that's an expensive solution. You've got all the materials you have to buy. You've got new piping, you've got clamps, you've got fittings, and then you've got the labor to tear out the old and put in the new. You have to dispose of all of those materials you took out. You got all these sealers that have to be properly disposed of as well. But most of all is the time involved, because this was a quick turn. And all the time that you're doing this construction work, you're not producing product. So not only are you spending money, you're not making revenue. So this is not a good solution, even during a product changeover. So we looked at this and we said, well, if temperature is the fundamental issue that we're dealing with, maybe what we can do is we can deal with it by controlling the temperature in the first place. Now, we know that temperature has an effect on dispense. We've already talked a lot about it. But this is a real good example of how it manifests itself. We've already said that the robot can control speed, distance, angle to the surface, path, even the pressures and the flow rates and the volumes dispensed on each particular pass. But that doesn't mean that we get the same results. In fact, if we look at this hem flange bead right here, what we'll see is that we have almost double the width at 38 degrees that we do at 16 degrees. What isn't evident from this is that these are exactly the same volume. They were put down by exactly the same robot. And so at 16 degrees C, the bead is significantly taller than it is at 38 degrees C. It's flatter. Because of the lower viscosity, when it was dispensed, it collapsed. Now, if it's fallen so far that it doesn't fill the gap between the two parts, we're going to have a failure. So it's extremely important that we dispense exactly the right amount of sealer in exactly the right places at every time. And if we want to get that perfect bead, and we're doing it with a robotic system that has no eye-hand coordination, it's essential to dispense the sealer at exactly the right temperature, which is to say exactly the right viscosity. And to do that, we have to control the sealer temperature as it's being dispensed on the part. And we call this point of application temperature control. Now, how we go about it matters. And this is one of the pedestal systems from the Tata Motors system. And from here we can see that the original integrator has put an electrically heated hose in that runs from the filter housing and valve all the way up to the gun. Now, this means that we're always bringing it up, we're heating the material, and we're sending it very close to the point of application at the same temperature. This would appear to be point of application temperature control. But things aren't always what they seem. Over the years, we've developed point of application as a process. And we define the process as follows. 1, think backwards from everybody else. 2, acknowledge that the only material that we care about is that which is actually being applied to the part. 3, start at the point of application and then work backwards, adding temperature control until all conditions can be met. And then stop. That's the amount that you need. Now, everybody laughs about number 1, think backwards from everybody else. But in reality, it is not at all uncommon to take a drum heater or a drum jacket or a heat exchanger right after the pump and send the material, the sealer, at exactly the right temperature out through that length of piping and expect that it's going to be at the right temperature when it gets to the other end, discounting all of the changes that we know are going to take place because of ambient. But in this instance, that's not where the integrator went wrong. In this instance, where they went wrong was at step number 4. They put temperature control at the point of application. Well, kind of. What they didn't do was work backwards, addressing all conditions to make sure that everything was stable at all points in the operations cycle, at all points in the year. So we still believe that there was a solution. In working with the Tata Motors body shop crew, we decided that we would apply some of our patented technology, and this is what we call a trace cover. This is a flexible trace cover, and we combine that with what we call our profile trace covers, which is a hard cover. These are very similar to one another, but they do somewhat different functions. We'll notice here that we have the blue ripstop nylon covering a layer of Nomex insulation. And this Nomex insulation is the same stuff that was developed by NASA for spacesuits to send men to the moon. This is pretty good stuff. When you wrap that around a pipe or a hose or any other device, it isolates it from ambient. Now we have to remember that insulation doesn't stop thermal loss, it just slows it down. So, in this instance, what we've done is we've taken polytubes and run them through tube pockets sewn into the inside. And then we circulate temperature-conditioned water or glycol through here to change the temperature of the air around the hose or the pipe or the device. What that does is the insulation isolates from ambient. The circulating water changes the temperature of the air around the device and creates a new ambient at or near the temperature of the sealer inside the hose or pipe. What this means is that there's no thermal gradient across the wall of the pipe or hose. And if there's no thermal gradient, there's no movement of energy. And if there's no movement of energy, then there's no change in temperature. So now we have a maintenance system. Now that's a little different from the profile trace technology. Here we can see that the profiles are actually formed to be the radius of the outside of the pipe, the header. We still have the same isolating structure going on, but basically having the copper in contact with the steel of the header turns that header into a tube-in-tube heat exchanger. And now we can actively change the temperature. When we put these together, we can now work in line, we can work around corners, we can work overhead, we can go any direction that we need to go and make the changes that need to be made. And those Velcro closures that they're made with makes it very easy to install them. In fact, they can be installed without ever cutting into the pipe. That takes care of the header systems. And we felt that that would address the pressure drops that were creating the line stoppages. But we still have to address the point of application requirement to make sure that the bead is consistent. For that, we looked at the electric hose. Electric hoses are great, except we're in Pune. It gets to be over 40 degrees there. At some point, if you're going to dispense the sealer at its optimal temperature to create the proper bead profile, you're going to have to do some cooling. And the problem with an electrically heated hose is it doesn't cool. So we removed it and we replaced it with this technology, which is what we call a coaxial hose. And it is a high pressure hose surrounded by another hose. And then we circulate water through this annular space in between. Now the blocks on the end are uniquely configured, and they not only hold the hoses in a coaxial configuration, they also provide a port where we can put a probe, a temperature probe, right in the material just as it exits the hose. This gives us control to feed back to our system at the point of dispense. So, how did this turn out? when we did the install? Well, here we can see that we went in and we inserted right at the beginning, the first thing that the system got was one of our profile trace covers. This put a heat exchanger right at the beginning. And then we spaced them at intervals throughout the header runs. And we interconnected them with the flexible tubing to go over clamps and around corners to give us a complete envelope surrounding the header that would give us a different ambient, a controllable ambient. And that took care of the header. For point of application, here's that same dispense system, and here we can see that we've brought the coax hose in, and we're circulating water through that, and we can see right here that the probe is right in the material just as it enters the gun. But to us, that's not enough. That's almost point of application, but not quite. So we created a flexible cover with tubes flowing through it to circulate water through here so that we could get all the way down to the point of application. Now we have a complete temperature control envelope. The whole thing was powered by a small temperature control unit. This is freestanding, it's on wheels, and it's great because it's both heating and cooling. It's fully automatic. You punch in the temperature that you want it to be going to the dispense head, and it holds it there. And in this configuration, it not only holds it there at the point of dispense, it holds it back all the way back through the header system. With that kind of stability, we were hoping that it would reduce the variation, reduce the pressure drops, and give us the stability that they were looking for. So the result? Well, the header cover system stabilized the sealer temperature regardless of swings in natural ambient. And this gave us a constant viscosity throughout the material delivery system. This produced the stable pressure drop we were looking for in the header system, and that presented a constant pressure to the regulators. This eliminated the pressure faults in the line stops that were plaguing them originally. So that was the first step that we set out to achieve. But none of that does any good if the beads aren't reliable. Now, the point of application tools that we put in gave a stable sealer temperature at the gun, again, independent of swings in natural ambient. This gave us a constant viscosity supplied to the gun. Coupled with the elimination of the variation caused by the line stops, this gave us stable, uniform, and predictable dispenses independent of day to night or season to season temperature variations, all without cutting into the pipe, all without doing a lot of damage to the system. We called that a success. Now, I want to thank you for coming back from coffee and joining us for this. And though we've only really scratched the surface of fluid temperature control for viscosity control, I hope that this has given you a little bit of a different idea of how this stuff works and maybe a different way to view your operations and the operations of your customers. So hopefully later we'll get a chance to have some questions during the dinner and the social hour, and we'll address those then. Thank you very much.
Thank you.